explaining reaction rates, and we're going to do this by talking both about collision theory and then using Maxwell-Boltzmann distribution graphs to explain why we see how the different factors have an effect on the rate of a reaction. Collision theory. So collision theory is essentially saying that for a reaction to happen, you're going to have these particles collide with each other successfully. And so in order for this collision to be successful, there's two things that have to work out. One of them is the geometry, and so it has to have the correct angle. So you can think of a molecule, it could be turned in different ways. It has to be facing the right direction when it collides with the other one. And then the second one is there has to be enough energy in the collision to get that to happen, because if you're breaking a particular force, so easily to think of a molecule being held together with covalent bonds, if you're going to be breaking those covalent bonds in order to create some new particle, you're going to need a certain amount of energy to break that attractive force between the currently attached atoms. So any factor that influences either the geometry or the energy of a collision will have an effect on the rate of reaction. So think of the geometry. If these particles here are to collide with each other, there is a chance that the two chlorines could form a bond between each of them, and you'd form chlorine gas and leave nitrogen monoxide behind. But the geometry is going to have to be correct. If the oxygen hits the chlorine instead of the chlorine hitting the other chlorine, then the reaction's not going to happen. And so the geometry has to be correct. Plus, if the energy has to be right as well, because the chlorine has to be broken off of the nitrogen, that's going to require a certain amount of energy to get that to happen. So we need correct geometry and we need correct energy to get the reaction to occur. 5 factors that actually affect rates are concentration, and essentially with concentration is if you have more collisions because you have more things there, the chances of having a successful collision are going to be greater. Temperature is going to increase the rate of reaction because higher temperatures are going to have, again, the particles moving faster, so they're going to have more energy and you're going to have more collisions, and so again a greater chance of having a successful collision. Surface area is essentially the same thing as concentration on a particle scale. So essentially you're just increasing the chances of collision, and therefore you're increasing the rate of the reaction itself. Catalysts we're going to look at in more detail, but these guys essentially lower the energy needed to break apart bonds, and so you don't need as much energy to get the collision to be successful, so they will speed up the rate of reaction. And then the nature of the reaction is important as well, because maybe the bonds aren't that stable to begin with. So loosely attracted particles are going to be easier. They're going to require less energy in order to break apart, and therefore to get them to react with something else would require less energy as well. So surface area and concentration. Let's look at this in a little bit more detail. Imagine we have 2 boxes here with some particles in them. If we have, so the same size box, this one here has 12 particles in it, and that one there has, the one on the right has 16 particles in it. So this has the lower concentration on the left and a higher concentration on the right, and so there's just more particles available to collide. There's more collisions happening, and so the rate is going to be faster for the one that has a higher concentration. Just more collisions, faster rate. Surface area, though, is really the same thing. On a particle scale, concentration and surface area are the same thing. And so take a look at this. We've got on the left, we've got 12 particles available to react. So there are here, it's a 4x4 block of particles. So there are 16 there, but it's only the ones on the outside. There's 12 particles around the outside, so like the 4 there, and then we have these guys up there, and these guys down there, and those guys down there. So we're going to have 12 particles on the outside of this block, and they're the ones where other particles could come in and react to them because they're on the outside. The 4 on the inside aren't available to be collided with because they're stuck on the inside there. So low surface area is essentially the same thing as low concentration on a particle scale. When you increase the surface area, so you spread the particles out, it's essentially the same thing as increasing the concentration as well, because now instead of just having 12 particles that are available to react with other particles coming from the outside, you now have 16 particles that are available to react. So on a particle scale, concentration and surface area are essentially the same factor. Transition state theory. So what this is saying is that during a successful collision, there's this intermediate species that is formed that's kind of halfway between the reactants and the products. And so if you think about a reaction happening where you've got to break some bonds and reform some new ones, this is kind of like in the middle. And so we call this the transition state, or the thing that gets created we refer to as the activated complex. And it is really high energy because you're in the process of breaking bonds and you haven't yet formed any new bonds entirely. And so it's going to be quite high in energy and very short-lived. It's kind of in the middle of the reaction. And the energy needed to reach this transition state, or to create this activated complex, is referred to as the activation energy. So think of a potential energy diagram. We've seen these before where you have your reactants and they form your products. And so the delta H between these two would be a negative delta H, because the reactants have more energy than the products. So the difference between the two is moving down in terms of the potential energy. And so think of this as a potential energy graph. This is what we've seen before for an exothermic reaction, but what we need to realize is that on the way from the reactants to the products, we've got to break up some bonds that are holding the reactants in their current conformation or current state, whatever they happen to be. And so we have to put in some energy. Then we're going to get out some energy after the new bonds are forming or the new attractive forces are forming. But this point in the middle is going to be always higher in energy. It's always going to require some amount of energy to do. And so this energy required to go from the reactants up to the activated complex, that energy is the activation energy, or energy needed to create the activated complex. If it's an exothermic one, again, the reactants have more energy than the products, so our delta H is going to be a negative delta H. But there, we must realize that we can't go directly to the products. We also have to put in a certain amount of energy, and that is the activation energy required to get to this activated complex, which is just some sort of species in between the reactants and the products. So in this case here, N2O is reacting with NO, and so essentially we are moving the oxygen from this molecule onto that molecule. So this activated complex would be some sort of thing where your N2O is breaking off that oxygen and is getting attached to this already existing NO, and it's sort of this thing that exists that's really high in energy that is halfway between what it was and what it's going to be. So imagine something like that. So if we're starting with our N2O and our nitrogen monoxide, you'd get this weird looking complex here, which, there's a better picture than one I drew, which is not quite the reactants and not quite the products yet. It's this weird activated complex, the transition state, high in energy. And then eventually you get your products. EA forward is going to be some amount, and the delta H is going to be the energy that you get out, because this is an exothermic reaction. There is the reverse process as well. So if you took the energy required to get to the activated complex, that EA forward, and you took the delta H that was the total delta H for the reaction, you could say, okay, well, if I wanted to go backwards, if I wanted to go from the products back to the reactants, I would have to go back up this hill and back down again. And so the energy required would be the sum of the delta H and the activation energy required to make the transition state. All right, let's look at the endothermic one quickly. Again, we would be starting with a set of reactants that is lower in energy, ending with a set of products that's higher in energy. And to get to the activated complex, we would need an EA forward because we're moving forward through the reaction. This would still have a delta H, which would be the difference between the energy of the reactants and the energy of the products. In this case, it's a positive delta H because we're putting the energy has gone higher from what it used to be. As the reactants, it's lower. As the products, it's higher. And so if we did want to go backwards, we would just have to put in this amount of energy here. Oh, that's a little high. This amount of energy here to get back to the activated complex. So that would be the EA reverse, because that would be the amount of energy required to move from the products back to the reactants. To get back up that hill, you'd need that amount of energy. All right, catalysts. Two different types we're going to mention. A homogeneous catalyst is one that is in the same phase as the reactants. So if you have a liquid catalyst and it's working on an aqueous species, that would be a homogeneous catalyst. Or if you had a gaseous catalyst that was in its gas state and it was working on gases, that would be a homogeneous catalyst in the same state or phase as the reactants. A heterogeneous catalyst would be a different one. So if you're driving around in a gas-fueled car still, the gas is being burnt and the emissions run through a catalyst. The emissions are a gas themselves, but the catalyst that we use to make them a little less harmful is a solid, and so that would be an example of a heterogeneous catalyst. What these catalysts do is that when you're doing your reaction, so again, we're starting with reactants. So let's say we're looking at a exothermic reaction. So the reactants have some amount of energy, the products have some lower amount of energy. Our delta H is going to be a negative delta H because the products have less potential energy than the reactants. And normally what would happen is the reactants would have to put in a certain amount of energy. So normally this amount here, that is your activation energy forward. It would be some amount. But what a catalyst does is it says, okay, well, let's try a different route. Let's try another mechanism or a different pathway, doing things slightly different. We're still starting with the same reactants and ending with the same products, but we're going to go through some alternative pathway, and it could be broken up into several steps, or maybe it's just one alternative step. But whatever it is, in order to get the products, its EA is going to be less. And so if we looked at the EA with the catalyst, it would be some amount less than the EA without the catalyst. So the reaction and the delta H is not affected, but the pathway to get to the products is going to be easier or require less energy. It may have more steps to it involved or something like that. It may somehow make it easier to break the bonds, but in one way or another, it reduces the activation energy needed to get to the products. Maxwell-Boltzmann distribution graphs and reaction rate. So a Maxwell-Boltzmann distribution graph is essentially a plot of the energy of particles, and we're plotting how many particles have a particular amount of energy. So the number of particles is on the y-axis and the amount of energy is on the x-axis. And this is for a particular given sample of a particular substance. So these graphs can be used to explain a whole bunch of different things about the properties of matter. We're going to be considering what their use is in explaining the rate of reactions. So we know a potential energy diagram. We know that the reactants have a certain amount of energy, and then this is an exothermic one. The products have less energy, and so during the course of the reaction, the reactants become the products. The difference between those two energies are delta H. We know that in order to get the reaction to happen, we've got to put in a certain amount of energy. That's our activation energy. So we do all know that about the amount of energy involved in a particular reaction. What we have been neglecting is that we've been saying that this amount of potential energy for the reactants is one amount. But the problem is that's not entirely true. When you have a sample of matter, not every particle in that sample of matter will have the same amount of energy. And a Maxwell-Boltzmann distribution factors this in. Because remember, if you have a sample and you take its temperature, we know that the temperature is the average kinetic energy. And so we can think of this energy that we're talking about as being sort of like the average amount of energy that the reactants have. But if it's an average, what that means is some particles have more energy and some particles have less energy. A Maxwell-Boltzmann distribution shows us that distribution of energy. So it's going to end up looking like this. We're going to have, again, the number of molecules is on the y-axis. And so very little molecules at the bottom, lots of molecules at the top. And the kinetic energy, or often not labeled on the bottom, is the speed of the particles, but we're going to express that as kinetic energy. And that's labeled on the bottom. So over here would be 0 kinetic energy, and over here would be, oh, that's the wrong way. Infinite amount of kinetic energy somewhere further down the x-axis there. And so if you were to plot this kinetic energy of molecules, what you'd see is that some of the molecules have a little bit of energy, some of them have lots of energy, none of them have negative energy, that's not a thing, but some of them have very, very little, just above 0, and some of them have lots of energy, and this is going to continually approach the 0 amount, but get less and less. But what we see is that most of them have an average amount of energy. So when we say that the reactants have a certain amount of potential energy, if we're referring to their kinetic energy or their temperature, this is what it would look like. Most of them would have a particular amount of energy. So let's say you had a glass of water sitting on your table there. Most of them would have about 25 degrees Celsius worth of energy, but some particles would have greater energy and some particles would have less energy. A Maxwell-Boltzmann distribution graph tries to show that distribution of energy. It looks very similar to a bell curve that you'd see in terms of students with particular grades. Most people would be somewhere around the average. There are some students that are higher, but the number is much less. And there's some students with a lower grade, and again, the number gets less. It is a nice, almost a normal distribution, almost a bell curve type curve. So concentration and surface area is a factor that affects the rate of reaction, and we know by increasing the concentration or increasing the surface area, which is on the particle scale essentially the same thing, by increasing their concentration or surface area, we increase the rate of reaction. The question is why? So if we look at a potential energy diagram again, so potential energy, and imagine this is the progress of the reaction. If it's an exothermic, they start with some energy as reactants, they end with less energy as products, and they need to overcome a certain amount of activation energy. So they'd have to get up to the activated complex, and there's some amount of energy that needs to go in, and that is the activation energy required to do so, so that the reactants can become the products. That activation energy could correspond to a certain amount of energy on our Maxwell-Boltzmann distribution. So imagine, often when they're on here, they're called the threshold energy, but imagine there's a certain amount of activation energy that is required. So imagine this is the activation energy required to do the reaction. For a given sample, some of them will have enough activation energy. So these guys right here, they do have enough activation energy. They can go through with the reaction because they have enough energy to do so. But the rest of them, these guys over here, don't have enough energy, so they can't do the reaction. What you do when you increase the concentration is imagine we have a second concentration here in, actually let's do green. Second concentration in green. If this is representing the energy of the sample, if we had a larger sample, so if I drew a larger sample, it's essentially the same curve, just it has a greater area underneath this because the area under the curve is essentially the amount of particles you're dealing with. So if I had a greater amount of particles, what I can see is right now there's more particles that have more energy than is required to do the reaction. So by increasing the concentration, I essentially get a greater amount of particles that have the right amount of energy to overcome the activation energy barrier and complete the reaction. So increasing the concentration, or the surface area, same thing, increases the amount of particles which have the necessary energy to complete the reaction, and therefore the rate of reaction will be faster. Temperature, a little bit trickier to understand, but again, same thing. There's going to be some again, potential energy. Let's imagine an exothermic reaction. There is some amount of energy that needs to be overcome to allow this reaction to go from reactants to products. And so there is a activation energy here that is needed for this reaction to happen. And this would correspond to some place on our graph here. And again, we could think of that as being the activation energy, or sometimes called the threshold energy. But it is the energy required to go from the reactants to the product. Now, let's say this is a certain temperature. So remember, the energy, this is going to be, let's call it T1, and it's a low temperature. Now, if we increase the sample, so let's say this is, I don't know, a cup of some solution that we have. If we heat it up, we don't get any more. So we're not going to, like when we concentration, we actually had more of the particles. But when we heat something up, we don't get more of it. We have the same amount. So you can kind of think of it as if this is a string. It's fixed on the zero point of the axis. So if we were to increase it, essentially we need to move the curve further to the right, because it'll have higher kinetic energy. So we're going to, if we have a second temperature in which we heat the substance up to, we're going to move the curve to the right, but it's fixed at the 0 point here, and we can't increase the surface area underneath it. So let's do this in orange as the second temperature. So essentially what happens is the curve sort of flattens out a little bit and moves over. Now the average temperature is higher, so T2 at a higher temperature is higher, because remember the average is the temperature, and this average is higher in kinetic energy than this first T1 one was. So we are increasing the temperature. The curve looks like it's lower, but remember the y-axis is the number of particles, not energy, because we're not increasing the sample size. We're essentially just pulling on this tail over here and pulling it along further, and so the curve is going to get a little bit lower down. And anyways, in terms of the rate of reaction, initially at the first temperature, the lower temperature, only this amount of particles down here had enough energy to overcome the activation energy to get the reaction to happen. But at the higher temperature, we now have all of these guys. We have more particles that are beyond the threshold energy or the activation energy needed to get the reaction to happen. So by increasing the temperature from T1 to T2, more particles are able or possess the required energy to overcome the barrier, allowing them to become products, and therefore, if more of them have the necessary energy to get the reaction to happen, the reaction will happen faster. Catalyst. So again, quick potential energy diagram. Actually, I think I have a better one here. Oh, look at that. That's much better. Okay, so we have this activation energy that's required. Now, a catalyst, what a catalyst does is it lowers the activation energy, so you don't need quite as much. So imagine, let's do the original one in purple. So we have this original amount of energy required, and then we have this catalyze. So that would show up on our graph. We'd say, okay, well, maybe this was the original energy required, the threshold energy or activation energy required to do the original pathway. What a catalyst does is it provides another pathway, and we see this on our potential energy diagram, that has a lower activation energy. So this EA2 is a secondary pathway, some other way that the catalyst provides, and essentially it's like moving the threshold energy required to a lower point. And so this EA, let's call it 2, or the catalyzed activation energy, it's an ugly line, but it is going to be lower down. And so essentially, originally, only a few particles had the necessary energy. But if you lower the bar, as with many things, more people are going to be able to achieve it, or in this case, more particles are going to be able to overcome that barrier. So a catalyst lowers the activation energy, allowing for more particles to perform the particular reaction that you're talking about, speeding up the rate of reaction. Nature of reactants. we know that some things are more reactive than others. So let's imagine that, I don't know, this is a piece of gold, let's say. Oh, that's not gold. Let's go gold. And imagine this is a piece of iron. So you buy your car and it happens to be made out of iron. Iron will oxidize, and that particular reaction has a certain activation energy. So to get iron to oxidize, let's say it requires a certain amount of energy, so that's the EA activation energy to get iron to oxidize. So there's a bunch of the iron particles that will have the necessary energy to do that reaction. Because they're iron, they have a certain amount. Now gold would have, it could also oxidize, but its activation energy might be much higher for that to happen. So very few of them will have the necessary energy in order to do that. So essentially, when you're looking at nature reactants, you have to consider two different situations. They're two different substances, and so they would have different requirements to do a particular process like oxidize. And if something is less reactive like gold, the reason why it's less reactive is the particular thing that you're trying to do is more difficult to do. It's like having a higher threshold energy, higher activation energy to get that task to happen. Something more reactive like iron, it is more reactive because the activation energy to do that task is lower down, and therefore more of the particles in the sample are able to overcome that activation energy and do the reaction.